Alright, so this is our fourth pre-lecture video for Monday's lecture. Just some disclaimers. If in the future you hear any weird noises during the video, it might be this guy, or it could be this guy. It probably isn't this guy. Alright, now let's get to it. What I wanted to talk about today is I wanted to spend some time talking about the concept of an electric field. It's sort of an abstract idea, and so I think it takes a little bit of time to sort of get what we're talking about. So in physics, we use the term field, which is really a shorthand for saying force field. Basically, a field is something that permeates space. But we can't see it, it's invisible. But the way that we know that it's there is if you put something in that area where the field is, the object will feel a force. And that's why we call it a force field. So in physics, in our first year of study, we probably will look at three different fields. The gravitational field, the electric field, which is what we're going to focus on today, and then in the future, the magnetic field. So first of all, let's just talk a little bit about the idea of the gravitational field. Let's say here is the surface of the Earth. We know that if we place an object here at some distance above the ground, it will feel a force down due to the force of gravity, and that's equal to m times g. Now, we have explained that force as the attractive force that the Earth is exerting on that mass, but there is another way to think about it. We could think about the fact that because the Earth does exert forces on objects, we could think of it as being due to a gravitational field that permeates the space around it. What I'm doing right now is I'm illustrating or allowing you to visualize the gravitational field. The arrows indicate the direction that the field acts in. And the way that we calculate the gravitational field is it is actually equal to small g. So it's equal to big G, in this case because we're dealing with the Earth, the mass of the Earth, and because we're close to the surface, the radius of the Earth squared. And so this is another way of expressing or explaining why this object feels a force down. We could say when it's placed in the gravitational field, a force is exerted, which is equal to the mass of the object times the gravitational field. So, now let's start talking a little bit about the electric field. So far what we've done is we've said that if we have two charges, Q1 and Q2, and let's assume they're both positive charges. Coulomb's law allows us to explain the force that exists between them. If they are some distance r apart, we could say that the force on 2 due to 1 is to the right, and the force on 1 due to 2 is to the left, because they repel each other. And we simply say that it's due to the Coulomb force, and this is how we calculate how large the force is. And so this is, again, very similar to the example for the gravitational field. So what we're going to say is there's going to be another way to explain the electric field. What we can say is we could explain it as the effect of the electric field that is due to one charge. So that's saying that a charge will create an electric field near it, and when another charge enters into it, it feels a force. So again, what we are saying is that when you place a charge in space, that charge will influence the region around it and it creates an electric field in that region. We can't see that electric field. We can draw lines to sort of illustrate it for ourselves, but we see its effect when another charge enters into it. And the way that we see the effect is that that charge that enters into the electric field will feel a force. So, let's say I have some large charge, some large positive charge right here. Now, if I allow a small charge to come near it, and I'm going to call this charge Q naught, and we are going to say it's positive. Because both these forces are both of these charges are positive, we'd say that this small charge is going to feel a force like this. And we could explain that force as a consequence of the Coulomb's law. Or we could say that what's happening is that there is an electric field that's extending away from this charge. And the reason that this charge feels a force is because of that electric field. So, how do we actually define the electric field? There is a way that it's actually defined. So we start off again with some charge right here. And then the way that it's defined is we talk about a little test charge, and the test charge is always positive. And so we'll call that Q naught. And of course it feels a force, and this is the direction of the force. The electric field, the definition of that is the force that that test charge feels divided by Q naught. And so, because we know how to calculate that force, the force that that test charge would have felt would have been K big Q, Q naught over R squared. If the electric field is the force over Q naught, and it is a vector as well, you can see that that'll end up to be K big Q over R squared. So it only depends on the charge that creates it. That's the electric field, only depends. And because we can also determine the direction of the electric field because we put a positive test charge in here, it ends up being in the same direction as the electric force. So in this case, the electric field is outward. Let's look at two different cases where we're thinking about an electric field created by a positive charge and then by a negative charge. Now we've already done the positive charge, and so this is going to be sort of short. Here's Q naught, which again, remember, is positive. The electric field is the force divided by Q naught. Now we know that this is the direction of the force, so it's also going to be the direction of the electric field. Now, if we make this charge negative and we put our Q naught near it, which is still positive, this will feel a force like this. It's an attractive force. And the electric field, which is the force divided by Q naught, will also be in that direction. So we actually end up getting a conclusion that is useful to us. The electric field points away from a positive charge points towards a negative charge. And so here we see it illustrated. What I didn't get to show very well in previous pictures is for a point charge, the electric field is radial. It radiates away from, outward from the charge that's causing it. And we could understand that because we could be putting Q naughts at any of these locations, and you would understand that that's the direction of the electric field you would get. Similarly, we see then for the negative charge, the electric field is coming in radially towards the negative charge. That's a little thing that's really helpful to remember, that the electric charge goes away from positive charges and towards negative charges. And here is the expression that we found for the electric field in a few slides ago, but it might not look quite the same because you notice that there's this 1/4 pi epsilon naught, and that might not look familiar. They're introducing this electric constant, which is going to come up eventually, but I think this notation is a little bit confusing. This epsilon naught has a value of 8.85 times 10 to the minus 12, but it turns out that 1/4 pi epsilon naught is equal to our K, our Coulomb constant. So this expression could very easily just be expressed as K Q over R squared. Remember, the unit vector R hat means that the field is in the radial direction. So because of this expression, the electric field is equal to the electric force divided by Q, we can also sometimes just say, hey, if I place a charge in an electric field, it'll feel a force equal to the charge times the electric field. This is something that we don't remember too much. This might be also a good time to talk about units. Since force is in newtons and charges in coulombs, one of the ways that we can express the units for the electric field is newtons per coulomb. All right, so we're going to finish with a simple problem. So if I have a mass of 3 grams, so here's my mass, and I'm placing it in a uniform electric field of 30 newtons per coulomb, which is pointing down. This is the direction of the electric field. I want to know the magnitude and sign of the charge that the mass must have so it can be suspended in air. Okay, well, we know that because it has mass, it feels a force down equal to mg. Now, basically, the question is telling us that I also need a force up due to the electric field, which is going to be equal to Q times E. If it's in equilibrium and the sum of the forces in the y direction are 0, Fe minus Fg have to be 0, or the two have to be equal in magnitude to each other. So QE is equal to mg. So using this, we can calculate the charge, which is going to be mg over E, which is 3 times 10 to the minus 3rd times 9.8 times 30. And let's do the numbers really quickly, because I forgot to do this calculation earlier. So I'm going to get 0.001 coulombs. I think it's a little rounded off, but that's okay. And what's the sign of the charge? Well, notice that my electric field is pointing down. This is down, but my force is up, which means that this is going to have to be a negative charge. And so the charge is actually going to be minus 0.001 coulombs. And that is how we use this, or just one example of how we might use this to do a problem.